Ever pick up something like a metal spoon, let's say, and wonder how something so solid, so strong, comes from something so incredibly tiny, like atoms?
It really makes you appreciate the power of those atomic bonds, doesn't it?
It totally does. And that's exactly where we're headed in today's deep dive. We're cracking open Tecnologia y Ingeniería 2, which, fun fact, is a Spanish engineering textbook.
Oh, interesting. I always love seeing how these fundamental concepts translate across languages.
Right. And that's what's so cool about physics and engineering those formulas. They're universal.
Absolutely. The laws of physics don't care what language you speak.
Exactly. So even though our source is in Spanish, we can still unpack some seriously cool insights about how engineers predict the strength of materials.
Ready to dive in. Where do we start?
Well, our textbook jumps right into atomic arrangements with these detailed diagrams of face-centered cubic, body-centered cubic.
Yeah.
It's a lot to visualize.
Ah, yes, those classic crystal structures. They can seem a bit intimidating if you haven't thought about them since, well, maybe ever.
Right. So for those of us who haven't been staring at atomic structures lately, what's the key takeaway here? What's the big deal about how atoms are arranged?
Imagine you're building a tower. You could just randomly throw bricks on top of each other, but chances are it wouldn't be very strong, right?
Probably not going to win any architectural awards.
Exactly. But if you arrange those bricks in a specific pattern, like interlocking them, you suddenly have something much more stable and sound.
Okay, so it's all about finding the most efficient way to stack those atomic bricks.
Precisely. Yeah. And that's where those diagrams and the concept of atomic packing factor come in.
Yeah.
They help us visualize and quantify how efficiently atoms are arranged in a material.
So like a material's atomic blueprint dictates its strength.
Exactly. Take carbon, for example. You can arrange those carbon atoms one way, and you get graphite, the stuff in pencils. It's soft, easy to smudge.
Yeah, definitely not using that to build a bridge.
Right. But now rearrange those same carbon atoms in a different, much tighter configuration, and boom, you've got diamond, one of the hardest materials on Earth.
That's wild. Same ingredient, totally different properties just because of how it's put together.
Precisely. And engineers have figured out how to measure this packing efficiency with something called the atomic packing factor, or FEA as it's called in our Spanish textbook.
Okay, so FEA tells us how tightly those atoms are jammed together. But what's the practical implication of that? Why should our listeners care about how efficiently atoms are packed?
Think about it this way. A higher packing factor generally means a denser, stronger material. Take tungsten, for example, the stuff in light bulb filaments.
Hmm.
It can withstand incredibly high temperatures without melting.
Yeah, those things get crazy hot.
Exactly. And it's because tungsten has a really high packing factor.
Cool.
Its atoms are arranged in a way that makes it extremely durable.
So it's like the atomic equivalent of a super tightly woven fabric. It's not going to rip easily.
That's a great analogy. On the other end of the spectrum, you've got something like gold, which is incredibly malleable. You can hammer it into incredibly thin sheets.
I've seen those gold leaf decorations. They're like impossibly thin.
And that's because gold's atoms are arranged in a way that lets them slide past each other easily. So it's all about those atomic bonds and how they influence a material's behavior.
So we've got strong and sturdy tungsten, super malleable gold, and everything in between. It's amazing how much variation you can get just from rearranging those tiny building blocks.
It really is. And understanding atomic packing is just the first step. To really predict how a material will behave, we also need to consider how it responds to stress and strain.
You're talking about those formulas I see here for
Yeah.
stress, strain, Young's modulus E. Those always seemed a bit, well, abstract back in my physics class.
Let's try to bring it back down to earth then. Imagine a car tire versus a trampoline. They're both designed to handle force, but in completely different ways, right?
One's all about support, the other's all about bounce. Totally different vibes.
Exactly. And those formulas you mentioned, stress, strain, and Young's modulus, they help us put numbers to those vibes, to
Okay.
quantify those differences.
Okay, I'm intrigued. Break it down for me.
So stress is essentially a measure of how much force is being applied to an object. Strain tells us how much that object deforms or changes shape under that force.
So, like how much a car tire compresses when you drive over a bump, or how much a trampoline stretches when you jump on it.
Exactly. And then we have Young's modulus, which is a measure of a material's stiffness or resistance to deformation.
Okay, so a car tire, which needs to be pretty rigid, would have a high Young's modulus, while a trampoline would have a much lower one. It's starting to click.
You've got it. And the cool thing is that these aren't just arbitrary concepts. We can actually calculate these values using those formulas.
So it's not just about saying this material seems strong, it's about putting a number on it, right? Quantifying it.
Exactly. And that's what allows engineers to predict how materials will behave in the real world, to design structures that are safe and reliable, from bridges to buildings, even down to the tiny components in your smartphone.
Wow, so those little formulas really are holding up the world around us.
In a way, yes. And it's all thanks to the power of material science.
You know, it's one thing to talk about stress and strain in the abstract, but our Spanish textbook gets really specific. I'm looking at an example right now that actually calculates the amount of force required to break a steel bar.
Ah, yes, those classic stress to failure calculations.
They sound pretty intense. In my everyday life, I don't really encounter a lot of steel bars on the verge of breaking, so help me see the relevance here. Why do these calculations matter?
Well, imagine you're walking across a bridge, just enjoying the view. You probably aren't thinking about the structural integrity of the bridge, right?
To be honest, not really. I'm usually too busy admiring the scenery.
Exactly. But somewhere, an engineer is breathing a sigh of relief because they used those exact calculations to make sure that bridge wouldn't buckle under the weight of all those people and cars.
So it's about having that certainty, that confidence that things are going to hold up as they should.
Precisely. And it's not just bridges. Those calculations are behind the scenes in pretty much everything we rely on, from buildings that reach for the sky to the cars we drive every day.
Wow, it really puts things in perspective, doesn't it? Those formulas aren't just scribbles on a page. They're literally holding up the world around us.
In a way, yes. And it goes far beyond just big structures. Think about airplanes, for instance.
Oh, right. Those things are under a lot of stress up in the air.
Exactly. The stresses and strains on an airplane wing during flight are immense.
I can only imagine.
And if the engineers get those calculations wrong, the consequences can be catastrophic. It's a huge responsibility. And those formulas give them the tools they need to get it right.
So it's really about safety at the end of the day, whether it's a bridge or a plane or even, well, you mentioned medical implants earlier, right?
Absolutely. Those have to be engineered to withstand incredible forces and stresses inside the human body, often for years on end.
It's amazing to think about the same principles that govern how a bridge stands up also apply to something as intricate as a hip replacement.
It really is. And that's the beauty of material science. It all comes down to understanding the fundamental properties of materials and how they interact with the world around them. And it's a field that's constantly pushing boundaries.
Okay, so we've got bridges, buildings, vehicles, medical implants. Are there any other surprising applications for these material science principles that our listeners might not expect?
Well, you might be surprised to learn that these very concepts are being used to develop what's known as self-healing concrete.
Wait, self-healing concrete? That sounds like something straight out of a sci-fi
I
movie.
don't know, right? It might sound futuristic, but at its core, it relies on those same fundamental principles we've been discussing: stress, strain, and the amazing properties of materials.
Okay, but how does concrete actually heal itself? Is it magic?
It's not magic, but it's pretty close. Basically, scientists have figured out how to embed tiny capsules filled with a special healing agent within the concrete matrix.
So these capsules are just hanging out in the concrete until they're needed.
Exactly. When a crack forms, those capsules rupture and the healing agent is released.
And then it just like magically fuses the crack back together.
Pretty much.
Yeah.
The healing agent reacts with the surrounding concrete, forming a solid bond that effectively seals the crack. It's like it never happened.
That is unbelievable. It sounds like science fiction, but it's real. It makes you wonder what other incredible material innovations are on the horizon.
That's the beauty of this field. Material science is constantly pushing boundaries, and who knows what incredible discoveries await us in the years to come.
We started this deep dive with a Spanish engineering textbook, flipped through some wild diagrams, and now we're talking about self-healing concrete like it's as normal as, well, a sidewalk.
And the truth is, even with all these mind-blowing innovations, we're really just scratching the surface of what's possible with materials.
It's almost like cheating, you know, taking these ancient, abundant materials like carbon, rearranging the atoms a bit, and boom, you've got something stronger than steel.
That's the allure of material science. It's about understanding those fundamental building blocks of the universe and then getting creative with them.
Speaking of getting creative, you mentioned graphene earlier. That stuff still kind of blows my mind. How can something so thin, so seemingly simple, be so strong?
It all comes back to those atomic bonds we talked about. In graphene, those carbon atoms are arranged in this incredibly tight hexagonal lattice. Think chicken wire, but on an atomic scale.
So it's like the ultimate microscopic chainmail. No wonder it's so strong.
Exactly. That unique structure gives graphene this incredible combination of strength, flexibility, and conductivity.
Okay, I get why they call it a super material now, but what are we actually going to do with it? Like, what's the real world potential of graphene?
Honestly, we're only just beginning to explore all the possibilities, but we're talking about things like super efficient solar cells, incredibly fast electronics, even water filtration systems that could provide clean drinking water to millions.
Seriously, it's like graphene is going to revolutionize, well, everything.
And here's the thing, it's not just graphene. There's a whole universe of undiscovered materials out there, combinations of atoms with properties we can't even imagine yet.
I suddenly feel like we need to start planning another deep dive, like right now, just to cover all this.
There's always more to explore, but for now, I think we've covered some pretty amazing ground. Who knew a Spanish engineering textbook could be so inspiring?
It's been an incredible journey, and I have a feeling that the next time I see a bridge or a building or even just a simple pencil, I'm going to see it in a whole new light.
That's the power of understanding materials. It changes the way you see the entire world.
Well said. Thanks for joining us for this incredible deep dive into the world of material science. Until next time, stay curious.